Hello and welcome to section 2.4, Quadratic Inequalities. This is going to be the section that kind of wraps up this unit that we have on quadratic functions and the kind of an overview of quadratics. So really in this last section of the unit, we're just going to be talking a little bit about things that we've done, but we're going to put a few things together. So a quadratic inequality in two variables. So we've got a quadratic inequality in two variables. It can be written in one of the following forms, where a, b, and c are real numbers and a does not equal 0. The solution set is a set of ordered pairs, which is x, y, okay? So these are your options. You have y on one side, you have your quadratic. It can be in standard form as presented here. It can be in vertex form. It can be in intercept or factored form. But these are the ways that we're going to be talking about inequalities. You have less than, greater than, less than or equal to, greater than or equal to. Okay, so previously we have solved linear inequalities in two variables by graphing. Well, we're going to use a similar procedure to do it with quadratic inequalities. So to graph a quadratic inequality, you're going to graph the parabola that defines the inequality or defines the boundary, and then you're going to use a solid curve when the ordered pairs on the line are included, so you'll have less than or equal to or greater than or equal to as solutions. If you don't have that equal to portion of your inequality, it's just greater than or less than, then you're going to use a dashed line, very similar to how we did it with linear functions. And then you're going to shade above the parabola for anything that's greater than, you'll shade below for anything that, okay? So again, a lot of stuff that we've already done before, just in a little bit different format, and there's examples of your shading and your solid and dashed lines there. So let's just do some examples. We're going to graph this and shade the correct solution. Well, doing this, we can look at this format and we can look at it one of two ways. This is either in standard form with no b term, so we have ax squared where a is 1 plus c, which is 4, or you can look at it in terms of a vertex form where we don't have anything in the parentheses with the x, so you just have x squared, which means we have no translation left or right, but we do have a up translation by 4 units. Well, we can use this information to figure out how we're going to graph it. If we were to look at this in vertex form, then we can find out what our vertex is. Well, we've got nothing inside the parentheses with the x, so we have 0, and then we have 4 on the outside. So our vertex would be 0, 4. It happens that's also our y-intercept, because if you look at this as ax squared plus bx plus c, the only c term, the c term is what we look at for our y-intercept, and that would be 4. So this vertex also happens to be our y-intercept because it falls on the y-axis. Okay, we can also look at our front term. A in any form tells us the same information, and that is it stretched or compressed, and is it flipped from concave up to concave down? Well, in our case, A is 1 because there's nothing in front of the x squared, so there's an understood 1 there. That means we're not flipped because it's positive, and we're not stretched or compressed. So from this information, really all we need is the vertex and the information that A gives us, and that's enough for us to figure out what's happening. So our vertex is at 0, 4, so that happens to be here. And then we are not compressed, we're not stretched, and we know we're concave up. So we're going to go over 1, up 1, over 2, up 4, and we can reflect this across our axis of symmetry. Since we have an equal to portion, then we can draw this with a solid line rather than a dashed line. And so we'll end up with something that looks like this when we graph the parabola. Okay? Now, the last thing to do is to figure out where we're going to be shading. Well, our shading is going to occur below the graph because we have less than. So everything below the graph will be shaded. So when you shade it, it's going to look a little something like this. Okay, let's move on to the next example. So we have this. Now this is in vertex form, so we can very quickly read off what the vertex is. So on the inside with the x, we have a -1. So remember, minus is the operation that's in our standard formula for vertex form. So our x is going to be 1, and then we have a -1 on the outside. So our vertex is at 1, -1. All right, so what else do we have? Well, we have a couple of other pieces of information. We have what the y-intercept is. If we plug in 0 for x, we can find the y-intercept. So if we take x being 0, what's left in the parentheses is -1. If you square it, we have +1, but we do have this minus out in the front. So that's going to be -1 minus another 1. So your y-intercept is going to be at y equals -2. And then finally, we have a on the outside here. And a in this case is -1. So it's not stretched or compressed, but it is inverted vertically. So it is a reflection across the x-axis, meaning that it's going to be concave down. All right, so let's plot our vertex. We've got 1, -1. So that's going to go here. And then we have our y-intercept at -2. Well, that's right here. And that makes sense because this is a standard parabola. So over 1, down 1. And we'll continue that. Over 2, down 4. And then down 9 from the 3. And we can reflect these on the other side of the axis of symmetry. So now we don't have an equal to portion, so we know it's going to be dashed. So we can draw a dashed line for our parabola. And then the last part is our shading. Since it's greater than, we're going to shade everything that's above the parabola. And so this is what it will look like when you shade the area above the parabola. Okay, let's move on to example 3. So example 3 is in intercept form. And with example 3 being in intercept form, we can immediately pick out what our x-intercepts are. And those x-intercepts would be x equals 3 and x equals -1. Well, it's important to find out what the x-intercepts are because we also need to find the vertex, and we're going to start with the axis of symmetry. And the axis of symmetry in a intercept form is p plus q over 2, wherein p and q are our x-intercepts. So we have 3 plus -1, so that's 3 minus 1 over 2. That's 2 over 2, which is 1. Now to find the other coordinate for our vertex, we're just going to plug in 1 into our equation up here, or our inequality, but we're going to state it as equation here since we're looking for a value. So we got 2 times 1 minus 3 times 1 plus 1. So that's 2 times -2 times 2, which gives us -8. So our vertex is at 1, -8. And then finally our a gives us one more piece of information. And that's 2, which means it's concave up, but it's also stretched by a factor of 2. All right, so let's start with our vertex. We've got 1, -8, so 1 over and then -8 down. So here we are here. And then we know we're stretched by a factor of 2. So we can go over 1 up 2 because we're doing the y times 2. So we'd go over 2 and up 8, and that happens to land us where our x-intercepts are, at -1 and 3. And we can go on with one more. Go over 3, up 18, which 18 is just 9 doubled. And now we look at the inequality. It has an equals to portion, so we're going to use a solid line. Okay, so that could have been a better job, but it will do for right now. Because the last thing we need to do is find the area that we're going to shade. And since we have greater than, we're going to shade the area above the parabola, and it turns out to be the area that's inside the parabola. And so this is the area that you would end up shading. All right, let's move on to example 4. Now we're going to graph this one and see what we get. So this is full standard form, so we can't use any shortcuts to find the vertex very quickly like we did with the first one, but we can still find the vertex using our axis of symmetry. And in this case, we're going to have to use x equals negative b over 2a. Well, b is negative 6, 2a, so a is negative 1. So be very careful. Make sure you don't lose any of your minus signs, okay? It's going to be tempting just to write negative 6 over 2 times negative 1 and forget this minus sign in the front even existed. So make sure you take care of all your signs as you plug things in. So we're going to end up with 6 over negative 2, which ends up giving us negative 3. We can find the other coordinate for our vertex by plugging negative 3 into the original. So you got negative 3 squared minus 6 times 3 minus 8. And then here we've got y equals negative 9, because 3 squared is 9. We got a negative out in front. This is negative 3, by the way, inside here. This is also negative 3. And then we have plus 18 minus 8. And so all this together gives us 1. So our vertex is at negative 3, 1. We could find the y-intercept if we wanted to. Because it's in standard form, the y-intercept is very easy to find. It would just be y equals negative 8 if you were looking for more information. And then our a here is going to be negative 1. That's our leading term. That's in front of our x squared. So this tells us that it's going to be concave down. Our vertex is at negative 3, 1. So negative 3, 1. So there's our vertex. So the 1 tells us with the a that it's not going to be compressed or stretched. So if we wanted to, we could just do 1 over 1 down, and then 2 over 4 down. And then the y-intercept gives us that last one that we can hit from 3 over 9 down. We've got no equals to part, so this is going to be a dashed line through the shape of this parabola. Let's see if I can do this a little bit neater on this side. Okay, and we'll put arrows on each side. And then finally, because it's less than, the area that's going to be shaded is inside the parabola or below the line of the parabola. So there's the area that would be shaded. All right, let's continue on and do a few more examples here just to kind of get this solid with what we're doing. This one is like the first one. We can use vertex and standard form to get all kinds of information. So first of all, the vertex is going to be at 0, negative 3. If we wanted a y-intercept, it would be very much the same thing. The y-intercept would be at y equals negative 3. It would be the same point as our vertex. A, our first term, is 1, so it's going to be concave up, and it is going to be a standard parabola. So we go down to 0, negative 3, plot that point, and we know it's going to be standard, so we're going to go 1 over 1 up, 2 over 4 up, 3 over 9 up, and we can reflect it across our axis of symmetry. Since we don't have an equals to portion on this, we're going to end up doing a dashed line for our parabola here. Okay. And then finally, since it's greater than, the area above the parabola is going to be shaded, so it's going to be what's inside the parabola. And so there's the area that we would shade. All right, let's move on down to example 6. Again, we've got intercept form, so the first thing that we can get right off is our x-intercepts, which would be x equals 1 and x equals -3. Let's see, we can do our vertex. First, we need our axis of symmetry by doing x equals p plus q over 2. P is 1, q is -3. So we've got -2 over 2, which equals -1. And then for our vertex, we're going to plug in to our original equation. So we've got -1 minus 1 times -1 plus 3. That's going to be -2, +2. So that ends up giving us 4. So our vertex is at -1, 4. If we wanted to find an x-intercept or a y-intercept, that's easy enough to do. All we do is plug in 0 for x. So we get -1 times -1, which is +1 times 3, which is 3. And then our a, that leading term, is -1. That's out in front right here. So that tells us that it's going to be a standard parabola, but it is going to be concave down. So we've got our vertex at -1, 4, which would be right here. We know it's going to be standard. We also know what our x-intercepts are, so we can go ahead and plot those. We've got 1 and -3. We can go ahead and plot our 1 over 1 down. And then maybe go 3 over 9 down. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can reflect that across our axis of symmetry. So since we've got an equals to portion, we are going to be doing a solid line. And so you're going to end up with a line that looks sort of like this, or a curve that looks something like this. And then finally, we're less than, so everything that's below the parabola curve will be what's shaded, which is everything that's on the inside of the parabola. And so there's the area that would be shaded. So you'll notice that none of these problems really take that long. A lot of it's kind of just picking out some of the key features of the parabola given the equation, and then using those key features to do our graph. All right, let's move on and do another. Here's example 7. So this is in standard form. So since this is standard form and we've got a b term, we can't shortcut it. So let's start with our axis of symmetry. So we've got x equals -b over 2a. That's going to give us negative times -4 over 2, and a is 2, okay? And so that's going to give us 4 over 4, which is 1. To find the vertex, we're going to plug 1 back into the original equation. So 2 times 1 squared minus 4 times 1 minus 5. That's going to be 2 minus 4 minus 5, which gives us -7. And so our vertex is at 1, -7. Our y-intercept's always easy on a standard form equation because it's just whatever c is. So c is -5, so that's our y-intercept. And then our a out in front is 2. So that means that we're concave up because it's positive, but we're also going to be stretched by a factor of 2. So let's do some graphing here. So we've got our vertex at 1, -7, so 1 and then -7. So that puts us right here. And we have a y-intercept at -5, so that helps us out a little bit. And we can reflect that. Well, if we go over 1 up 2, the next one's going to be over 2. Instead of up 4, we're going to go up 8. 1, 2, 3, 4, 5, 6, 7, 8. And of course, the axis of reflection allows us to do it equally to the other side. And we could probably go one more. Let's see if we can. So we're going to have 3, 18. I think we're going to be just one shy of being able to do that, but that's okay. We'll work with what we've got. We've got 5 points, so I think that's enough to work off of. So we don't have an equals to portion, which means that we are going to be using a dashed line. And since we have less than, it's going to be everything that's below the parabola, so everything that's outside of it. That's what we're going to shade. And so there is the area that would be shaded for this particular inequality. All right, let's do one final example like this before we move on to the last couple of sections here. All right, so this one we have in vertex form, which is great because we can go straight to where our vertex is without having to do really any work. Our vertex is at -2, 1, since we have minus -2 on the inside here and we have our +1 on the outside. All right, our y-intercept we could find if we wanted to, and let's go ahead and do that. The y-intercept would be, if we plug 0 in, we have 2 squared, which is 4, -4 plus 1, so that would be -3. And our a value out in front here is -1. So we're not stretched or compressed, but we are inverted. So if we have y is less than or equal to here, first of all, let's do our vertex, -2, 1. We know we're concave down. Our y-intercept's at -3, so there's that, and we can reflect that one. And we know we're not stretched or compressed, so we can go ahead and fill in some of these gaps here. And we go 3 over, 9 down. That puts us here. All right, we do have a equals portion, so that means we're going to have a solid line. And then finally, we have a less than, which means anything below the parabola will get shaded. So that would be everything inside the parabola. And there we are. That is the shaded region for this particular graph. Okay, so that is graphing inequalities, quadratic inequalities. Again, we're just taking things that we've already done and we're kind of putting it together. Now let's talk about verifying quadratic inequality solutions. So you can determine if an ordered pair is a solution to a quadratic inequality by substituting the values for x and y into it. If the statement is true, then the ordered pair is a solution. If it's false, then the ordered pair is not a solution. And so this is a very easy thing to do. Let's go ahead and start with this first one. So our inequality is y is greater than 2x squared plus 5x minus 4. We're going to take this ordered pair, our x and y, and we're just going to plug them in. So y is 4, x is -1, so we're plugging in -1 for x, and then we don't even have to touch the left-hand side. Let's just simplify the right-hand side and see what number we get. So -1 squared is 1, times 2 is 2. -1 times 5 is -5, and then we have minus 4. So we end up with 4 is greater than -7. And that is indeed a true statement. So that means that the ordered pair, negative 1, 4, is a solution. It's that easy. So let's do a few more of these. Well, here we have this inequality. Y is less than or equal to x squared plus 6x minus 3. Y is 5. X is 3. And we're just going to simplify this right-hand side and see how it relates to 5. 3 squared is 9. 6 times 3 is 18. And then you have minus 3 on the end. So you end up with 5 is less than or equal to 24. And again, yes, that is a true statement. So since it's true, 3, 5 is a solution. All right, a couple more of these. This one we have y is greater than x squared minus x plus 6. Y is negative 3. X is 2. So we're just going to substitute that in. So you end up with negative 3 is greater than 4 minus 2 plus 6. So negative 3 is greater than 8. And that is a false statement. So since that is a false statement, 2, negative 3 is not a solution. And then one more example. We have y is less than or equal to negative x plus 3 squared minus 4. Well, this is in vertex form, but that's okay. It's going to be the same thing. We're just going to plug in our y. We're going to plug in our x. And we're going to see what we get. Well, negative 4 plus 3 is negative 1. Negative 1 squared is 1. So you get negative 1 minus 4. Negative 8 is less than or equal to negative 5. And that is a true statement. And so since it's a true statement, then we can say that negative 4, negative 8 is a solution. All right, so now let's move on to the easiest part of all. Algebraically, it's easy. If it's false, then it's not a solution. If it's true, it is a solution. Well, what if you're presented with a graph and you want to find out if any of these are solutions? Well, if we plot the point, if it falls within the shaded area, it's a solution. If it's not in the shaded area, it's not a solution. Now, on the boundary, you have to be a little bit more careful because it will only be part of the solution if the boundary is a solid line. Okay, so let's take a look at example 13. So for example 13 here, we have the ordered pair negative 4, 2. Okay, and it asks us to determine if it's a solution, and if it is or isn't, whether either way we need to explain our answer. Well, let's see where negative 4, 2 is. So negative 4, 2 would be this point right here. And so it falls on the boundary, but the boundary is dashed, which means that any points along the boundary are not included as part of the solution. So this is how we would write our solution. So we would state no, that it is not a solution, and the reason being is because it lies along the boundary, but the boundary is not included as part of the solution. All right, for part B, we've got negative 3, 1. So let's see where that is. We have negative 3, 1 is plotted right here. And so that's clearly in the shaded region, so therefore it is a solution. So here's how we would write that answer. We would say yes, it is a solution. It lies within the solution region. And then finally we have 0, negative 2. So 0, negative 2 would be right here along the y-axis. And it's clearly not within the shaded region. So here's how we would write that answer. So we would simply put, no, it is not a solution. It lies outside the solution region. All right, let's move on to the last example in this section. And it's one like we just did. So here we are given the graph of the quadratic inequality, and we want to determine whether each of these ordered pairs is part of the solution. And again, we're asked to explain our answers. So we'll start with the first one. We have negative 4, 0. So negative 4, 0 would be right here along the x-axis, and it's right along the boundary. But again, the boundary is dashed, so therefore it is not part of the solution. So this is how we would write the answer. So we would say, no, it is not a solution because it lies along the boundary, but the boundary is not included as part of the solution. And that's because it's dashed. Now, if we go to 4, 0, 4, 0 is over here, and it's clearly in the shaded region. So there it is right there, right along the x-axis once again. And so here's how we would write this answer. You would state that it is a solution and that it lies within the solution region. Okay, now let's head on over to C, which is negative 1, 0. So here's negative 1, 0 right here, again on the x-axis. And this time we are clearly outside of the solution region. So we would write this. We would say, no, it is not a solution because it lies outside of the solution region. And we've got one final ordered pair here to take a look at, and that is 2, 6. So we go over 2, up 6, and we are clearly in the shaded region. So we would write this. We would say, yes, it is a solution because it lies within the solution region. So I think these are fairly straightforward. You basically see, is the point in the shaded region or not? If it's on the boundary, is it a dashed line or is it a solid line? And you may draw your conclusion from there. And where you find it, basically is your explanation as to why you answered the way you do. Okay, so this wraps up the final section of Unit 2. We will be pressing on to Unit 3 after this. And in Unit 3, we will be doing more with quadratics, and we'll actually be doing some solving of quadratics.